In the last section, we were learning how to calculate the average rate of a reaction. And we looked at a graph that kind of looked like this with a reactant and a product. And this would be a graph of their molarity versus time, or pressure versus time. And we were looking at how we could use this type of graph to calculate the average rate of a reaction. And we said that when we were calculating the average rate of a reaction, we were going to pick some particular time, like maybe this time right here, and we would just be calculating the change in concentration during that time and dividing it by the change in time. So it was going to be something along the lines of delta concentration, change in concentration, versus the change in time. And if it was for a reactant, we were going to put a negative sign in front so that the number ended up being positive. And we also learned if we had an actual chemical equation going that we could go off of, we would add, down here in the denominator, we would add the stoichiometric coefficient in order to make the rate equal for all of the reactants and all of the products in the reaction. And so while all of this is accurate, this type of calculation here is giving us, so all of this is giving us what we call an average rate. And the average rate that we're calculating has limited use. I don't want to say it's not useful, but it doesn't have a lot of use. It is time frame specific. So if we're calculating an average rate, we need to know a particular time period to do that calculation. So it's not, the average rate is not specific for a reaction in general. It's going to be specific for the first 30 seconds or the first 90 seconds or something like that. The average rate is not a constant. So let's make a list of why the average rate is not particularly super. The average rate has limited usefulness. And again, I want to emphasize it's not useless. We are still going to use it, but it does have limited usefulness, and the reasons is that it's not a constant. So if we calculated the average rate over the first 30 seconds, that number would not be the same as the average rate over the first 3 minutes. So it's time dependent, depends on the time frame. So it's going, let's say it depends on delta t. And the other, well, I guess this is all kind of the same thing. It's not really two separate things. The rate of a reaction changes during the reaction. And we can understand that by looking at our graph. Look at it again, and let's just focus on a reactant like this. So initially in the reaction, like right in this area right up here, initially where we have a high concentration of this reactant, we can see that its concentration is decreasing pretty fast, and that's because we have a lot of it. So in this area of the graph, like up here in this part of the graph, and during this particular time frame in the reaction, the rate of this reaction is very high, meaning that it's reacting quickly, because there's a high concentration of it. And as the reaction proceeds, so we get down into this area here where the concentration drops, and we're looking at this time frame, the rate slows down quite a bit because we have a smaller concentration of that reactant. So for the most part, when we're talking about how the rate of the reaction changes, the rate is usually very fast at the beginning of a reaction, and then it slows down as the reaction proceeds, as we use up our reactant. So because the rate of a reaction changes, we could say that it is concentration dependent. The rate of the reaction depends on what the molarity is of our reactants. It's more useful for us to calculate what we call an instantaneous rate. That's not how you spell it. Instantaneous rate. So instead of calculating the average rate, we would calculate the instantaneous rate. Let's compare it to average rate. The instantaneous rate, which a lot of times we will just refer to as rate. So if we just say rate, we're typically talking about instantaneous rate. It is concentration dependent. So when we're calculating the instantaneous rate, we are calculating, let me go back up to this graph right here. We would say, what is the rate of the reaction at this instant? Or what is the rate of the reaction at this instant? Or what is the rate at this instant? And those rates are dependent on the concentration at those particular times. Whereas the average rate depends on the amount of time that has passed when we are making the calculation. So the average rate depends just on the change in time. The instantaneous rate is much more useful because if we know an equation for calculating the instantaneous rate, we would be able to calculate the rate of the reaction at any particular time. So average rate is still useful, but it's less useful. The average rate is the one that we calculate using, we're just going to, for example, a reactant, so negative delta A over delta T. That's our average rate. For the instantaneous rate, it is calculated a little bit differently. And so we're going to kind of derive it first and then we'll fill it in. So for the instantaneous rate, which actually we call rate with a lowercase r, that's important. The rate of the instantaneous rate of a reaction is directly proportional to our concentration. Rate is directly proportional to concentration of A. What does that mean? That means if the concentration of A is high, like at the beginning of the reaction, then the rate is also high. And if the concentration of A is low, then that means the rate of the reaction is going to slow down and the rate will be low as well. So the rate is directly proportional to the concentration of A, and direct proportionalities are not super useful for calculations. So instead of using our direct proportionality, in order to turn this into an equality, we have to add a constant into this equation. And the constant that we use is symbolized with a lowercase k, and we call that lowercase k the rate constant. And again, this is just a number that is put into this proportionality in order to make it an equality. Used to make this guy into an equality. The value of the rate constant K is experimentally determined meaning that we just have to repeat a reaction over and over and over again, collect a lot of data, and come up with the value of K. It is dependent on the reaction. So it's not like the ideal gas constant, R. K is different for every reaction. So it's more like an equilibrium constant, capital K, big K. It's reaction specific, and it also depends on the conditions. So the K for a reaction at 25 degrees might not be the same as the K for that exact same reaction that's being run at 50 degrees. So when you are solving these types of problems, you're never going to consult some sort of data table or appendix to look up a K, very much like you would never look that up for a capital K as well. So let's take a look at how we would experimentally determine K. It's pretty straightforward. If we wanted to experimentally determine the rate constant K, we would just run a reaction, like I said, over and over and over again and measure the rate of the reaction compared to a whole bunch of different values of concentration of A. And what we would find typically is if the concentration of A is very low, then the rate is also going to be low. And if the concentration of A is very high, the rate will be high. And this will be a linear relationship, which is awesome. And so we can measure rate versus A. The slope of this line, because it's linear, is our rate constant K.